block of mass m starts from rest and slides without friction down an incline of angle theta in length L. Find the speed of the block when it reaches the bottom of the incline, expressing your answer in terms of g, L, and theta. So this is a quick diagram of what the situation we're given is. So this angle here is theta, and we have a block. It's mass m, and it's sliding down the incline. So let's start by perhaps drawing a free body diagram so that we can analyze the forces on the block. So downwards, we have the force of gravity, and since it's in contact with the incline, there's a normal force N, and it's sliding downwards. So now, let's take the positive x direction to be the direction it's sliding down. And again, this choice of axis and coordinate system is, you can choose any coordinate system you like. It just happens that this choice simplifies the problem. So let's start by using Newton's second law to, and let's write Newton's second law for this block to figure out what its acceleration is, and then we could perhaps use the kinematic equations to find its final speed at the bottom of the incline. So in this direction perpendicular is the positive y direction. So the sum of the forces in the x direction, which is along the incline, and this here, this angle is also theta. So from this, the force of gravity in the x direction is just mg sine theta. And that's the only force there since there's no friction. So we equate that to the mass times the acceleration in the x direction. Now for the y direction, we have the normal force in the positive y direction and the component of gravity perpendicular to the incline, which is mg cosine theta in the negative y direction. And since the block is sliding along the incline, that means it's not accelerating away from or into the incline. So our acceleration in the y direction is 0. So this whole right side is 0. So now we want to solve for the acceleration in the x direction so that we can use that in the kinematic equations. So all we need to do is divide by m on both sides. And this gives us that the acceleration, and I'm going to drop the subscript here, is just g times sine of theta. And this is a constant acceleration, which means that the kinematic equations apply, the main kinematic equations that we have learned. And specifically, we can use that the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the distance traveled. And we know that v naught is just 0 since it starts from rest and slides down, and we want to figure out the final speed. Now d is just L, which is the length of the incline it slides down, and a is given by what we derived here. So plugging everything in, we get that the final velocity squared, and again I drop the subscript, is equal to 2g sine theta times L. So all we need to do is square root the whole expression to get that v equals the square root of 2gl sine theta. And so this would be our answer here. But before we accept it, there are actually a few more checks that we can do to see if we're going in the right direction. And these checks will also let us know if we're definitely wrong. So let me just erase this. So the first check we will use is something called dimensional analysis. And that basically means that the units on both sides of the equation must be equal. So the velocity has units of meters per second, and that's on the left side. And now we need to figure out what units this quantity has. And so first, let's go through all of the symbols and variables in this expression. So we have 2, which is just a number, and it doesn't have any units, so we don't care about that. And then we have g. G is an acceleration, is the gravitational acceleration. So its units are meters per second squared, the same as any other acceleration. And then L here is a distance. It's a length along the incline. And distances just have units of meters. And finally, we have sine of theta. So this might be a little tricky, but notice that theta is just a constant. It's sliding down an incline with a constant angle of theta. And so sine of theta really is just a number. And it also has no units, so it's dimensionless, and we can ignore it as well. So the only 2 units with dimensions, or variables with dimensions, are g and l. And we carry the square root over as well. So now if we simplify these units, we get meters squared over second squared, and square root that, which is just meters per second. And this checks out with the units of velocity. So at least we know that we have some right combination of variables such that the units across the equation are consistent. So that helps us build our confidence in our answer. So another thing that we can check are limiting cases. So these are what happens at, say, maybe when this angle theta goes to 0. Since if theta equals 0, then you just have a flat surface and a block just sitting there. And you generally have better intuition for these limiting cases that you can check. So if it's just sitting there, we would expect that its final speed is just 0, since it's not really sliding down anymore. And we can actually check what happens as this angle theta approaches 0 of our derived expression for the velocity. So as theta approaches 0, the sine of theta also approaches 0. So since the sine of theta approaches 0, this whole expression approaches 0. And so the velocity approaches 0, just as we would expect. And we could also check what happens when, say, theta equals 90 degrees. In that case, it's really just the block falling vertically, just downwards. And in this case, we know that the acceleration is g, since it's just falling down. And again, if we apply our same kinematic equations, then we get that the velocity at the bottom is the square root of 2gl. So that's our expected answer. And now let's check it in this case. So let's see what happens as theta approaches 90 degrees of our derived expression. So as theta approaches 90 degrees, sine of theta approaches 1. So this whole expression just approaches square root of 2gl. And again, this matches what we would expect, as it's just basically free falling. So checking these 2 cases gives us even more confidence in our answer. And if one of our expressions, say, differed from what we would expect, then we know that we might have done something wrong and should go back and recheck our whole calculation. And one more thing we can check is, does this combination of variables make sense? So as g increases, then intuitively it would make sense that v also increases, since the force of gravity is stronger and it's pulling it down faster, and our equation satisfies that. And as L increases, we would also expect v to increase because it's being accelerated for a longer amount of distance, and this is satisfied in our equations too. So, and also note that there is another way where instead of using F equals ma, you could also do energy conservation. And this would lead you to the exact same answer here. Although it is more general in the sense that if you have an incline that's like, say, curved or something, then F equals ma would be much harder to apply since your acceleration is no longer constant. So that's just one thing to note. But at the end of the day, the answer derived here does turn out to be the correct answer. And that is how you would solve this problem here.